Good day! I am Sir Jason Alviar and welcome to Mathusay Math and Tutorial on Lesson 1, Introduction to Sequences. In this video, you will learn how to describe and generate patterns. Let's begin. Humans are naturally capable of recognizing patterns in nature and in the world, whether consciously or subconsciously. Early humans recognized the repeating interval of day and night, the changing of the season, the phases of the moon, and the rising and falling of tides. Understanding these patterns allowed humans to survive the test of time. Similarly, many flora and fauna hold mathematical marvels. The patterns of the seeds within a sunflower, the snail shell, and even how rabbits reproduce follow certain patterns. Do you also notice patterns around you? Can you cite other examples? Patterns are everywhere. We recognize them easily because patterns are regular, repeated, or recurring forms or designs. Consider this sequence of emoticons. Can you guess the next emoticon? In this sequence, we see an alternating happy face and sad face. So the next emoji should be a happy face. How about this? How many matchsticks are needed to form 4 squares? You see that we have 3 figures there. The first figure, with 1 square, it needs 4 matchsticks. To form 2 squares, you need 7 matchsticks. And to form 3 squares, you need 10 matchsticks. If you look at the pattern 4, 7, and 10, it gradually increases by 3, right? So, to look for how many matchsticks are needed to form 4 squares, you only need 13 matchsticks all in all. Now that you can recognize patterns, let's define sequence. What is sequence? Sequence is a function whose domain is the finite set 1, 2, 3, 4 up to n, or the infinite set 1, 2, 3 up to so on. We know that function is a relation. And when we say relation, you have a set of ordered pairs x and y. Now, a sequence is a function, and we know that function is a relation in which each element of the domain corresponds exactly to one element of range. It simply means that no 2 ordered pairs should have the same values of x. So let's consider this sequence 4, 9, 14, 19, and 24. This is defined by a certain function with a finite set of domain or values of x, the natural number from 1 to 5. So, because there are 5 terms in the sequence. Now, if n is equal to 1, the function will give you an output of 4, which is your first term of the sequence, or a sub 1, as we denote it. If n is 2, the function will give you an output of 9, which is the second term of the sequence. If n is 3, you'll get 14 as your third term of the sequence. When n is 4, you'll get 19 as the fourth term of the sequence. And lastly, if n is 5, you'll get 24 as your fifth term. Now, as you can see, this is an example of a finite sequence which has 5 terms in it. We also encounter sequence like 1, 3, 5, and 7. This is an example of an infinite sequence, which is defined by the function a sub n equals 2n minus 1. When we say infinite sequence, it means that you don't know what's the limit or the last term of the sequence, meaning it goes on and on forever. So, to clearly understand sequence as a function, let's take this sequence. Let's take the sequence and consider this 1, 3, 5, 7, and 9, which is defined by the function a sub n equals 2n minus 1. We know that when we say function, you should have a set of ordered pairs in which no two ordered pairs must have the same values of x. So, let's try to compute it and write it in a table of values and graph it to show you that sequences are really functions. So, if n is 1, a sub 1 equals 2 times 1, that's 2, minus 1 is 1. So, when you substitute n by 1, you get 1. Now, when n is 2, 2 times 2, that's 4, minus 1, that's 3. Now, when n is 3, 3 times 2, that's 6, minus 1, you'll get 5. When n is 4, you'll get 7, and when n is 5, you'll get 9. As you can see, no value of n repeated. So when you try to graph this set of ordered pairs, you have 1, 1, 2 and 3, 3 and 5, 4 and 7, 5 and 9, and then you graph it, you will have a linear function. Therefore, we have illustrated that sequence is a function. There are 4 types of sequences which will be discussed throughout the module. This includes arithmetic sequence, geometric sequence, harmonic sequence, and Fibonacci sequence. Now that it is clear to us what sequence is, let's have some examples. Our goal is to describe and generate patterns in the given sequence. Example number 1. What is the next term of the sequence 0, 4, 8, 12, and 16? And what is its 8th term? As you can see in the sequence, each term after the first can be generated by adding 4 to the preceding terms of the sequence. So you can see 0 plus 4, you get 4. 4 plus 4, you get 8. 8 plus 4, you get 12. And then 12 plus 4, you get 16. Then 16 plus 4, you will have 20. Right? So the next term is 20. Now, we have already 6 terms in the sequence. So, we want to find the 8th term. So, the 7th term is 24, and the 8th term of the sequence is 28. So, we can now describe the sequence as after the first term, each term can be generated by adding 4 to the preceding terms. So our answer here is the next term is 20 and the 8th term is 28. Let's have example number 2. What is the 6th term of the sequence? 1, 4, 9, 16, and 24. We can see that the terms of the sequence are all perfect square numbers. So, each term after the first can be generated by squaring n. So, we know that if n is 1, you have 1 squared, you still get 1. If you get 2 squared, you'll get 4. You get 3 squared, you get 9. 4 squared, you got 16. Now, we know that we're dealing with the 6th term. So, 6 times 6, or 6 squared, you'll get 36. Hence, the 6th term of the sequence 1, 4, 9, 16, 25 is 36. Example number 3. What are the next terms of the sequence 5, 10, 20, 40, and blanks? Now, the succeeding terms of the sequence can be generated by multiplying 2 to the preceding terms. You see that the first term is 5. When you multiply it by 2, you'll get the second term, which is 10. So, 10 times 2 is 20, or 20. So, that gives you the third term of the sequence. 20 times 2, you get 40. So, the next term should be 40 times 2, you'll get 80. And 80 times 2, you'll get 160. Therefore, the 5th and the 6th terms of the sequence is 80 and 160. Let's have example number 4. What is the 7th term of the sequence? 40, 29, 18, 7. We see that the terms of the sequence are decreasing by 11. So, since our first term is 40, 40 minus 11, you get 29. 29 minus 11, you get 18, which is the third term. 18 minus 11, you get positive 7. And then, since there are only 4 terms in the sequence and we want to get the 7th term, so we continue the sequence by adding negative 11. So, 7 minus 11, you get negative 4 as your 5th term. Negative 4 minus 11, you get negative 15. And then, negative 15 minus 11, you get negative 26. Therefore, the 7th term of the sequence, 40, 29, 18, 7, is negative 26. Example number 5. What is the 10th term of the sequence 1, 1, 2, 3, 5, 8, and 13? As you can observe, each term can be generated by adding the 2 preceding terms. You see, the first 2 terms, 1 and 1, when you add, you get 2, the third term. When you add the second term and the third term, you get the fourth term. When you add 2 and 3, you'll get the fifth term, and so on. So, to get the 10th term, we have 7th term already, right? So, to get the next term, 8 plus 13, you'll get 21. 21 plus 13, you get 34. 21 plus 34, you get 55. Therefore, the 10th term of the sequence is 55. This is an example of a Fibonacci sequence. Please pause the video and try these exercises, and don't forget to type your answers on the comment section. If you have learned something from this video, give it a thumbs up, share, and subscribe to my YouTube channel. Remember, ang sikreto para maging math husay, matuto, at mag-ensayo. See you all on the next lesson. God bless us all.